Hi, everyone. Let's take a look at thermodynamics for Chem 26. I'm going to review some of the lecture notes of Professor Season, and I'll just add my 2 cents wherever I can, try and help clarify things. So here's our thermodynamics handout. Start the PowerPoint slide. There we go. Cool. Get the pen going. Nice. Okay. So thermodynamics, study of energy in chemistry. We'll start off with the definition. Let's look at, where's my pen? There it is, off screen. All right, try something else. That's better. Okay, so we got spontaneous versus non-spontaneous processes. Okay, spontaneous just means something that's able to go all by itself. It does not mean fast. So in common language, like you're sitting around on the couch, friend walks by and says, hey, let's go to the movies. You know, this is before COVID. That's spontaneous decision, kind of quick, unexpected. In chemistry, that doesn't carry the same meaning. Spontaneous just means something, a reaction, or just a process that once it gets started, it happens all by itself. How about a fire? That's a spontaneous process. Once you start, set something on fire, as long as there's fuel, it'll keep on burning all by itself. If you set a ball on the side of a hill, give a little nudge, it starts rolling. It'll continue to roll all the way down the bottom of the hill. Spontaneous process. You leave something made of iron outside in the rain. A few days later, it turns to rust. Spontaneous process, happens all by itself. There's some reactions, however, that just don't happen all by themselves. And those are non-spontaneous. Okay. Turn off the pen so we can go on. Hello. There you go. There we go. And sorry, we'll still have to work with all these little nuances of online learning. There we go. Okay. Here's an example of something spontaneous. If you fill up a balloon with hydrogen gas, hydrogen is actually explosive. It's flammable. Mix it with oxygen, set a spark to it, and it'll burn, it'll explode. Hydrogen gas plus oxygen. And the product is actually water, a very stable molecule. So you get a lot of energy coming out. Something that doesn't happen all by itself, non-spontaneous. If you just have liquid water, doesn't just spontaneously separate into flammable hydrogen gas and oxygen gas. That doesn't happen. So under normal conditions. So that's a general trend that we see in nature. There are some reactions that only like to go one way. So hydrogen gas plus oxygen makes water. That's spontaneous, happens all by itself. The opposite, start with water, it doesn't spontaneously break down to form hydrogen gas and oxygen gas. Not spontaneously, not all by itself, but you actually can get it to happen non-spontaneously as long as you apply an input of energy. Oh, forgot to show this part. Actually, no, we can tie it in right here. So there's a nail, nice clean nail, leave it outside for a while and it turns to rust all by itself, going from top to bottom, spontaneous. But we never see a nail just naturally unrust and turn back to pure metal. No, that's non-spontaneous. You can, however, add energy, like the battery here, and cause water to break down. It's not a spontaneous reaction. It doesn't happen all by itself. You need a constant input of energy. So you can force the reaction to go backwards. You can force a non-spontaneous reaction to take place. The chemist would say is that you've coupled 2 chemical reactions together. You have this reaction here where the electrodes, you can see the bubbles. One test tube is forming oxygen gas, the other one's forming hydrogen gas. Can you tell which one's which? The answer is yes, by the balanced equation, right? So we're driving the hydrolysis of water. Two water molecules are breaking down to form two molecules of hydrogen gas and one molecule of oxygen gas. So you're getting twice as many gas molecules in here than in here. So you know which one's which. That's kind of cool. Anyways, back to coupling the reactions. We have this reaction taking place within the beaker through electricity. And inside the battery, there's a series of reactions taking place too. The reactions in here are spontaneous. They just form naturally to produce electricity. And the electricity is being used to drive this reaction backwards, right? The spontaneous reaction is where you burn or combust hydrogen gas and oxygen to make water. That's a spontaneous direction. Happens all by itself, a little spark, kaboom, form water. But with the input of energy, as soon as you turn off the energy, it stops. The reaction will stop, right? It'll stop bubbling because it's not spontaneous. But still, neat trick here. You can force it to go backwards. Something in biology happens all the time, right? So if you think about metabolism, eat some food, your body digests it and gets energy out. What do you do with that energy? Well, part of it goes to making new tissue, new blood cells. You're actually building up molecules similar to what you just broke down in digestion. Yeah, it takes an input of energy to create these big molecules. And if you take those big molecules in your diet, proteins, carbohydrates, your body can break those down, get energy out, and take the energy and make new carbohydrates and new proteins for your body. Cool. All right, back to the PowerPoint slides, maybe. Did I stop it? Sorry, wrong slide. We'll get there eventually. There it goes. There we go, right here. Okay. Next page, please. Okay. Now the question is in chemistry, which reactions are spontaneous? Those that happen all by themselves, and which ones are non-spontaneous? And more importantly, can we predict from a chemical equation which ones are going to be spontaneous and which ones are not? Well, it turns out it's not so straightforward. But here's some trends. Most spontaneous processes proceed with a decrease in energy. Sometimes that's exothermic, right? So I said the fire was spontaneous. Once it's lit, it keeps going until it burns up everything. And fires are definitely exothermic, giving off energy. So maybe that's the key. And the answer is no, not the complete picture. Spontaneous reactions are usually or often exothermic, but not always. Okay, so this is an example I said about the explosion. Hydrogen gas, oxygen, spark, makes water, lots of heat energy comes out. But let's ask this question. Which of these is spontaneous at room temperature? So that's the key. At room temperature, let me get the pen going again. Room temperature might be 25 degrees Celsius. Which of these is spontaneous? Well, kind of break down the formula here. Here's water in the solid form, or a better word for that is ice. And then this is water in liquid form, it's turning to water. And then this one is water turning into ice. And so if we're at room temperature, which one is a spontaneous process? This one, ice melts at room temperature. Now, is that an endothermic or an exothermic process? Well, for ice to melt, it needs to absorb heat energy to turn into liquid water. And the delta H, the enthalpy change is positive, which means it's an endothermic reaction. Well, this actually is not a reaction. Reactions change reagents into new products, but we just got water, H2O turning into water, H2O. So I call this a process, not a reaction. So I would say it's an endothermic process. So got a delta H, an enthalpy change, positive meaning it's endothermic. And if you want water to change to ice, you have to take away the heat. You must force water to be exothermic and release heat energy so it can cool off to harden up to ice. Hey, if you're at negative 10 degrees, now which process is spontaneous? This one is. Water spontaneously forms ice if you're below 0 degrees Celsius. And then this one would not be spontaneous at negative 10 degrees. Ice doesn't melt at low temperatures. Ooh, so that's another trick here. Instead of adding energy to switch a reaction, we could change the temperature. That's kind of cool. Okay. Here's another, just throwing it out there, something else that's spontaneous. What if you have two flasks? One is under vacuum. There's nothing in here. You open up the valve. The left side has gas molecules. That's what little circles are. And spontaneously, they spread out. Why do they do that? Well, just nature. That's tendency to just kind of spread things out. This actually does not take any energy to do that. It just naturally will just, nature abhors a vacuum, I think it's been said. It's just a natural process. It spreads out. Okay, that is actually a big clue as to, another clue, I should say, as to how we can predict whether a reaction is spontaneous. The first clue is many spontaneous reactions, not all, but many of them are exothermic. Second idea here, the second trend, is that there's something here about just spreading things out naturally. Ooh, I'm having trouble. Do I still have Zoom? Sorry, computer's doing something weird. Okay, let's stop the recording, pause it just briefly, just make sure everything's okay. Still recording, still good. Sorry for the delay. Let's go back, continue on. Okay. Let's make sure I didn't skip a page. Nope. Okay, so we had those two ideas, spreading out naturally and exothermic. So here's the idea about spreading out naturally. Yeah, some factor other than energy is important to the spontaneity of process. So we said most spontaneous things are exothermic, but not all of them. So something's more important than just energy. It appears that greater, more universal dispersion, all this stuff. The second idea, trying to be described here, is something called entropy. Entropy is a measure of randomness. It's a measure of disorder. And that's kind of weird to think of it, but it's a natural thing that happens in the world around us, right? Things tend to go from order to disorder, right? So if you're on the beach, you build a sandcastle, beautiful thing, it takes a lot of energy to create it. Come back later and it's falling apart, someone stepped on it, the wind, the waves, something's crashed into it and spread all that sand around and just made a mess of things. You clean up your house, takes a lot of energy to do that. Come back in a week or something and it's a mess again. It just naturally goes to disorder. And the same thing is true in chemistry. And it could be just simple things like this. You neatly packed one flask with all the gas, the other side is empty, nice, neat, and orderly. Someone open up this valve and mix things up. Now it's more disordered. And that's the way nature tends to drive. You'll never see these two flasks with gases in it just spontaneously fill up one side and empty out the other side. That's just not natural in our universe. So that's something called entropy that we use to describe this natural thing, natural state of things going into disorder. Cool. Okay, and then we can put some math on it. So it's another state function. State functions are those functions that, whoa, I tapped the screen. State functions are those functions where it doesn't matter how you get there, Just matters where you start and where you finish. And if you know the values of those two, you can calculate the difference. And it doesn't matter how you get there. So enthalpy, delta H was that way. Delta S is this way. Potential energy is that way. So you think about climbing a hill. If you go straight up the hill, you raise your potential energy. And if you decide to go spiraling up the hill, but you go to the same top of the hill, you have the same amount of potential energy as a person who walks straight up. So it doesn't matter how you got there. You only think about where you started, down at the base of the hill, and where you ended, top of the hill. And that's enough to calculate the potential energy, because potential energy is a state function. Okay, that's what delta S is here. Now, this is really important. We kind of, hopefully you have a sense, just in everyday life, you can look at something and say, that's messy and needs to be cleaned up, or this one's nice and neat and orderly. So you probably already have a good sense of order and disorder. So then just remember, entropy is a measure of randomness, disorder. So if things are really, really messy, then entropy, S, delta S really, is going to have a large positive value. Okay, now let's look at some chemistry examples and think about randomness from that point of view. So down here in tiny print, why is it so small? We got a crystal in this flask, and then it becomes a liquid, and then it becomes a gas. Is this going from more randomness or less random? Well, you start with crystal, everything's nice and neat and orderly. They're equally spaced, tightly packed together, nice order crystal. It's very neat and orderly, very low random, very low entropy. But you melt it, and now these molecules are all over the place at the bottom of the flask. That's more random. And then if you heat it up even more, it goes from liquid to gas. Now look at these molecules. They're everywhere. It's like all over the place. Where are they? Anywhere. If it was a solid, you know exactly where they are, or approximately where they are. They're at the bottom of the flask, neatly packed together. If you know where one of those molecules are, you got a good idea the other ones are right nearby, because it's all packed together as a solid, neat and orderly, low entropy. The gas, though, if you know where one gas molecule is, you have no idea where the others are. They could be anywhere, completely random. Cool. Okay, so the phase is one thing you want to look at: solid, liquid, or gas. Gases, high entropy; solids, low entropy; and of course, liquids will be in the middle. Temperature. Okay, so at higher temperatures, the particles have greater freedom to move around. It's when we talk about gases that we'll realize that temperature of gases is proportional to the kinetic energy of the gas molecules. And all we're saying is hotter gases, the molecules move faster. And it's also true in liquids and solids. So as a solid, the little molecules are stuck in a crystalline solid, but they can vibrate in place. And so at really, really low temperatures, they're not vibrating very fast at all. You warm up some ice before it melts, and the water molecules start vibrating a little bit faster, not enough to break loose, not enough to melt, but the water molecules can move and vibrate faster in place inside the ice. And then you can reach the point where you heated them up, the molecules of water are vibrating fast enough that now they can unstick and move away from the crystal, and they'll slide around as liquid water. It melted. And the more you heat up the liquid water, the faster the particles move around, stir about, bounce around, diffuse. You heat them up enough, now they can unstick from the neighbors and jump up into the gas phase and totally bounce around all over the place. So that's the second factor. Look at the temperature of the substance. With higher temperature, it's going to have the ability to spread out more, move faster, be more randomly located wherever you start. Yeah, so it's much more random. The type and number of particles that make up a substance. So if you can see the small font N2O4, there are 6 atoms in that molecule. And then it breaks down to form 2 molecules of NO2. One molecule only has 3 atoms in it, and there's 2 of them. Okay, so what's more random? Having one molecule with all 6 bouncing around, or having 2 molecules bouncing around? Yeah, it's much more random to have 2 molecules than just one molecule bouncing around. I also like to think of it as, hey, if you know where one oxygen atom is out of N2O4, that one oxygen is pretty close to the other 2 nitrogens, the other 3 oxygens. You got a good idea where they are. Not so random. If you know where one oxygen is and you know their structure, you pretty much can figure out where the others are. But if you have NO2 and you know where one oxygen is, well, there's the second NO2 molecule that you have no idea where it's at. It's much more random. It could be bouncing around anywhere. Okay, so as you increase numbers of molecules, numbers of particles, that's more random. And if you get everything grouped up into one big molecule, that's more neat and orderly, less entropy. And then variations in the type of particles. We got ions down here. I think that's what they're trying to emphasize here, that you have, I still think of this as a solid breaking down into individual ions. It's much more random, right? If this is NaCl, salt, the salt, sodium, and the chlorine, they're in a crystal of, a salt crystal. They're all tightly packed together, neat and orderly, low entropy, but once they dissolve, they can go anywhere in solution. There you go. Okay, so some factors to think about. Ooh, so here's a little self-check. Now first, I know Professor Season probably did this a little differently. I'm gonna do some of them, and then I'll leave the rest of these for you to carry out in the discussion, in our weekly discussion on Canvas. And we can discuss these answers there. Okay, so let's try the first one. Actually, these are pretty close, pretty quick. Maybe we'll just do them all. Where's my pen? Solid carbon dioxide going to gaseous carbon dioxide. Wow, my pen's not working. There we go. Maybe not. Anyways, is this a process that's increasing or decreasing entropy? It's becoming more random, right? Solids are more packed orderly, gases are not. So delta S is positive, more entropy. What about this one, letter B? We got one molecule becoming 2. Ooh, more molecules, more random. But we're also starting with a solid, and we create a gas. Gases are more spread out. They can occupy more space and much more random. Yeah. What else we got? We got nitrogen gas, hydrogen gas, 4 molecules total, becoming 2 molecules. Wait, there's fewer molecules. We're starting to group things up, make some neat and orderly things here. We have fewer molecules. It's easier to keep track of all the atoms if there's fewer of them. This is more orderly. Delta S is negative for letter C. Iodine solid going to iodine aqueous. Well, as a solid, they're all nice and neatly packed together, all the iodine in a solid, but now aqueous, they're spread out throughout the liquid. Yeah, much more random. There we go. Laws of thermodynamics. The first law, I think you probably heard before, it's the total energy is constant, right? You can neither create nor destroy energy. And then we're going to start talking about a system, usually a chemical reaction, and its surrounding. So like the solvent, the beaker, the laboratory, and actually you extend it to the whole rest of the universe, could be the surroundings. And we're saying, hey, add up all the energy before and after, it's going to be the same. It's constant. That's the first law. The second law is now tying in this idea of spontaneity. If you have a spontaneous process, the total entropy, the measure of order or disorder of a system and its surroundings always increases. And that's what we see in our world around us. Things that are spontaneous, usually exothermic, but they're also usually going from a process of neat and orderly to more random, more spread out, more distributed. That's the second law. Okay, correctly predicting the spontaneity of a process or reaction requires us to consider entropy changes for both the system and the surroundings. So there's some neat tricks here that we can do to figure out whether a reaction or a process is spontaneous or not. And part of that trick is separating what we're investigating into a system, like I said, usually just the reaction, and the immediate surroundings. That's what the italicized print down here at the bottom of the screen is saying. Usually it's focused on the immediate surroundings, like the solvent that the reaction is being taken place in. But technically the surroundings is more than just solvents, the beaker, the bench top, the laboratory, planet Earth, the solar system, the entire universe. Yeah, we won't have to go that far every time. Ooh, okay, I really want the pen to work now. Let's see, how about if I get PowerPoint's pen going? Yes, okay. Although I just scratched the screen. Yay, why doesn't it work? There we go. It's already set. Okay, so we got a couple things on the screen here. We got delta S of the surroundings, and that little alpha means proportional. Let me put a couple other ideas up here. If you're not familiar with proportional, here's the idea. If you go to work and you get a paycheck, you could say your income is proportional, that's a little alpha there, to the hours worked, right? So the more hours you work, the more income you get. It's directly proportional. Income, however, is inversely proportional to your sick days, unless you get paid for them. We usually don't. Like if you don't go into work, call in sick, your income's going to go down. More sick days means less income, inversely proportional. That's what the little alpha means, proportional. So what we discovered through studying just everyday life, that the craziness, the disorder of the surroundings is proportional to what is this saying? Okay, delta H of the system is the heat of reaction, right? And so delta H of the system is negative when exothermic. I think of a fire, be the fire. I am the fire. I am an exothermic reaction. I'm giving off heat and life, and I'm just turning the ash into nothing. I'm releasing energy. My energy is going down as I release all that heat to the environment. So I'm the system, I'm the fire. My heat energy content is decreasing as I burn. Where's that heat going? To the surroundings. So the entropy change, the craziness, the disorder is proportional to how much heat is being released. Now, if you're the fire, you're giving away energy to the environment, right? So you're heating up, like you have a campfire, everyone holding their hands over the fire is absorbing heat energy. It's the surroundings is absorbing, or it's a positive delta H. So we got this minus sign. Come on, pen, where'd you go? There it is. You got this minus sign. And if it's exothermic, your delta H is negative, and a minus times a minus makes a positive. And so delta S is positive if it's proportional to being exothermic, right? Where's that heat energy going? It's making the air molecules go faster and spread out. If you got a pot of water over the campfire, you're boiling it and making the water molecules turn to steam and spread out. Yeah, you're making the surroundings more crazy, more random. Okay, what else do we know? This one's a little more counterintuitive. You have to kind of think about it a little bit. The amount of disorder that changes is inversely proportional to the temperature. As a student, I struggle with that. But a teacher told me this way. Well, think about raising an ice cube just by a few degrees. add a little bit of heat energy to something that's at low temperature. And it can cause a big difference in randomness, right? So you heat up a little bit of ice and it melts. And now you got where the ice was water held in place, nice and neat and orderly. Now it melts and it's bouncing around in a liquid puddle. And it's just a few degrees of temperature difference. So a big difference. Now think about a hot oven and the gas molecules of the oven bouncing around at 400 degrees. And you crank up your oven to 450. Well, the gas molecules are going to go a little faster. But you get a big change in craziness and randomness. The air in the oven were already moving really fast at 400 degrees. Now they're moving a little bit faster at 450. They're a little more random. It's not a big difference in the amount of randomness, though. So that's the idea, is that at low temperatures, the randomness can change pretty quickly, large changes in entropy. But at high temperatures, the change in entropy doesn't really change as drastically. The cool thing is you put these together. The entropy of the surroundings is proportional to the heat of the system. Well, change the sign. And inversely proportional to the temperature. So put them together and you just get the enthalpy, delta H, divided by the temperature. And now you can calculate how much entropy increases or decreases in the surroundings for the whole universe. That's what this equation is saying. Okay. Turn off the pen. Actually, I want to erase the whole thing. There we go. Go on to the next slide, please. There we go. Okay, so you can now define the entropy of the universe is equal to the entropy of the system plus the surroundings. I hope that's pretty straightforward. If you really want to calculate the entire entropy change for the entire universe, you separate it to, well, how much entropy, craziness, randomness is changing in my system, and then somehow calculate everything else in the surrounding universe. Oh, wait a minute. We now can do that with that equation on the last page, right? We just said the entropy change of the surroundings is equal to the negative enthalpy change of the system divided by the temperature. And so you can actually calculate the change in entropy for the whole universe if you know the entropy change for the system and the enthalpy change, the heat of reaction for the system. The second law says that if your system is undergoing a spontaneous process all by itself, then the entropy change of the entire universe, that's the second law, should be increasing. If somehow the process is non-spontaneous, there should be a decrease in the universe's entropy, craziness, randomness. And if you're in equilibrium, saying that both the forward and the reverse reactions can go at equal rates, that's equilibrium, then there is no change in the randomness of the universe. That's kind of interesting there. Most of the time, though, second law of thermodynamics saying a spontaneous process is increasing the total entropy of the universe. Okay, rethink, move on. Move on. All right, let's try a little calculation here. We want to, well, consider the oxidation of iron metal, so rusting, by determining the sign of the entropy change of the universe. This somehow showed the reaction spontaneous. Okay, so this is where I wish I could confer with Professor Season, because I'm hitting a brick wall as to how you only look at the sign and determine this. But let's work this out as best we can. So pencil still seems to be working. First, let's look at the entropy change of the system. Is it positive or negative? Positive entropy change means more random as you move from products to reactants. A negative entropy change says things are becoming more neat and orderly. So what have we got here? Well, we got 4 atoms and 7 things becoming 2, performing fewer particles. That's less random. one of our reactants is a gas, everything's a solid. Ooh, that's even more orderly too. So the system is actually negative. It's more ordered. Or taking a gas, which is really random, saying, nope, no more gas, it's solid. And we're taking a whole bunch of things and saying, no, let's pack them all together and just get two things. And if the entropy is decreasing, usually that's not a spontaneous process. But wait, oxidation of iron, that's rusting. That is natural. So what's going on here? Well, I think this example is saying you can't just look at the system to determine spontaneity. You really should be looking at the universe or something else a little easier. We'll see in a few more slides. Okay, so let's break this down. The universe is split into a system. Well, why? And I can't erase that. There's an undo button here. And yay, technology. Nope. Ooh, okay, but I can't erase a single line. I'll remember that next time. All righty. Something's weird with my pen. I'm not gonna erase every single thing. Entropy of the universe is equal to entropy of the system plus the entropy of the surroundings. Entropy of the universe. Entropy of the, wow, system. Sorry about that. Technology is glitching. Minus the enthalpy change of the system over the temperature. So we just decided the system is negative. And then this term, the surroundings, I apologize for this glitching. This must be a really big positive number. So you have a large positive and take away a small negative. You need this side to be positive. The universe, the entropy of the universe must be increasing in order for this to be spontaneous. And I guess what that's saying then, T, the temperature, must be in Kelvin, which means Kelvin temperatures are never negative. So if you look at this term and you say, well, what's the sign of it? What's the algebraic sign? The T is always positive. Enthalpy, delta H, it's negative if it's exothermic. And if you multiply it times a negative, that makes it positive. And a positive divided by a positive makes it positive, and that's what we want. So what this says is that rusting metal must be a very exothermic process. Cool. I think that's what this objective was of this sample problem. Okay, let's move on. We can, if you have some questions, you can ask those in the discussion, and we can discuss it and try and figure this out a little more clearly if you have some questions. First law, energy is constant. Second law, entropy, the randomness of the universe, increases for any spontaneous process. Third law, as you lower the temperature, things become less chaotic, less random. In fact, if you go to a perfectly ordered crystal at 0 degrees Kelvin, absolute zero, we define the craziness of entropy to equal 0. So remember, there's no temperature lower than 0. What is temperature? Some say it's a measure of the particle's velocity. And so once it stops, you can't go slower than that. And so that's the idea. 0 degrees Kelvin, all molecular movement completely stops. And if you got them neatly ordered, everything's perfectly in order, 0 entropy, 0 disorder. So the third law allows us to say, hey, for a crystal at 0 Kelvin, entropy equals 0. And then if we want delta S, that's initial minus final, Well, now we got the initial point, which is 0. And from there, we can calculate the entropy of molecules and substances. So here we got graphite, natural form of carbon, and it has a entropy value of 5.740, and the units are joules per mole per Kelvin. We'll get into the reason why in a minute, but 5 here. Diamond is more orderly. It's a three-dimensional array. Maybe you can look up, Google structures of diamond versus structures of graphite. And if you look at the two structures, you'll see that diamond has much more order. It's more regular. The entropy is less. It's only 2.38. Whoa, carbon monoxide is 197. Carbon dioxide is 213. Why so high compared to 5 and 2? Well, they're gases. Gases have more entropy. Yeah, more disorder. Anyways, we actually have numbers now. We just say, hey, gases are more random than solids. Now we actually have values. We can do some calculations with them. So this equation looks crazy, but really it's just Hess's law. You remember Hess's law? Let's put it at the top here. Hess's law. If you wanted to calculate the heat of reaction, what you did is you took the heat of formation. Is it called formation? Yeah, I think it's heat of formation of the products. And you subtracted it from the heat of formation of the reactants. And you had to multiply these values of the heat of formations by the coefficient, right? For the number of molecules, you had to do that. And Hess's law works for calculating the energy change, and endothermic or exothermic, delta H. You use the same thing for delta S. Cool. So let's try it out. So instead of saying, hey, delta H of formation is some value, calculate the heat of reaction, now we're saying the entropy, standard entropy is some number, calculate the change in entropy for this reaction. And so use Hess's law, or the modified version now, the change in entropy is equal to the products, well, the S of the products, the entropy of the products, minus the entropy of the reactants. So what do we got? Delta S equals the product. That's NO2, which is right here. Wow, zigzag. It's 240.1, but there's 2 of them, right? So I should put a 2 here. There's 2 molecules, so each molecule has a standard entropy, crazy disorder measurement of 240.1, but there's 2 of them, so multiply by 2. And subtract that from the reactant, which is N2O4, dinitrogen tetroxide 304.4. And then do the math, 240.1 times 2 minus 304.4. The entropy change for the reaction is, this is number 3. I did the work ahead of time, try and save us some time. It's positive 175.8. And then the units, you'll be given the units, just tag them on to the end of your calculations. Mole to the -1 power means mole is in the denominator, and you multiply it times Kelvin. Hey, wait, this is positive. Does that mean there's more randomness or less? More. Does that make sense? If we didn't do the calculations, would we have predicted that this is making things more random? Yes, we start with 1 molecule and we created 2. They're both gases, but we have more molecules, more particles, more randomness. Yeah, so it makes sense that this is a positive number. Cool. Okay, I'll let you do this one. It's the same process. You can discuss it in the notes. In the discussion. I came up with a delta H equal to a negative 198.7 joules per mole Kelvin. So see if you get something similar. Hopefully I didn't make an algebraic error. We can correct it in the discussion. Here we go. Now let's tie things together. So delta H is whether it's endothermic or exothermic, sometimes called the heat of reaction. Delta S is entropy, the randomness, the craziness factor, times temperature. And if you multiply temperature times the entropy change the sign, add it to the enthalpy change, you get this new number called delta G, the Gibbs Free Energy. And it turns out that's a really good name for this. So if this is exothermic, heat energy is coming out, and that's available to do something. You can boil your water with it. You can warm up your hands. You can toast marshmallows with it. Heat is coming off. You can do something with it. And is it spontaneous? Well, if it's exothermic, maybe it is likely to be. If it's creating more disorder, it's very likely to be spontaneous too. So more entropy means this is positive, but we change the sign so you get a negative number here. Oh, remember, T is Kelvin. It's always positive. Can't have a negative Kelvin temperature. So this term will always be negative. This term will be negative when it's more random. That is, delta S is greater than 0 if it's positive. Then this becomes a negative term. Oh, why does it do that? And then delta H, if it's exothermic, it's also negative. So you have a negative and a negative. This nice sign right in here. Negative when spontaneous. That's the key. So remember, we started out these slides by asking, how can we tell when a reaction is spontaneous? Use Gibbs free energy equation, which I scribbled all over the place. Delta G equals delta H minus temperature times delta S. You'll get that equation on exams. It'll be very useful. If you calculate delta G, that's negative. It means the reaction is spontaneous. And that's what this slide says. Here it is, delta G negative, it's spontaneous as written in the forward direction. If you do this, if you use this equation and you discover that, hey, delta G is positive, then the reaction is not spontaneous. And what you can do is flip the reaction. The reverse reaction must therefore be spontaneous. Remember when we talked about ice melting at room temperature? So that's spontaneous. But if you go to negative temperatures, that's not spontaneous for ice to turn into liquid water if it's freezing. No, you switch this. Liquid water spontaneously becomes ice at freezing temperatures. So if you calculate the delta G to be a positive thing, it means, ooh, reverse your reaction. That's the one that's spontaneous and goes all by itself. So therefore, it's really important to remember that delta G needs to be negative to be spontaneous. And I had a student tell me, I have trouble remembering that. And someone else in the class said, well, think of it this way. If someone walks up behind you and scares you, what's your spontaneous reaction? You might scream, you might cry, you might get angry. It's usually a negative response. So usually spontaneous things are negative responses. And I thought, you know what, I'll try and remember that. So delta G is spontaneity. If it's negative, it's spontaneous. Cool. Hey, this is really cool. Delta G could be positive if it doesn't work spontaneously. It's negative if it is spontaneous. What about if it's neither positive nor negative? What if it's actually 0? It means it's in equilibrium, which means both reactions are spontaneous. So at 0 degrees Celsius, solid ice can melt. That's the melting point, 0 degrees. But liquid water can freeze because water freezes at 0 degrees. It's at equilibrium. They can go back and forth. So that's going to be very handy. If delta G is 0, you are at equilibrium. The reaction is reversible. You can go forward and backwards. And I just kind of preempted this slide. This one, take a screenshot or go back to the PowerPoint slides on Canvas and take a look at this. This is where you can just look at the signs of delta G, delta H, delta S, and make some predictions. I think they're pretty straightforward. Just the most important thing is, remember that delta G is negative. It means it's spontaneous. Delta H, negative, means it's exothermic. And then the kicker is switch it. Delta S, positive, it means it's more random, which is where nature tends to go. But then there's that minus sign in front of this positive entropy change that makes this number negative. So you have two negatives making a bigger negative, so it's more spontaneous. Cool. Did we just go backwards? We are going backwards. Let's go forward. Oh, and then we already talked about the neat trick. There are some temperature questions. They'll say, hey, calculate the temperature which the spontaneity reaction changes from spontaneous or non-spontaneous. Or at what temperature will this become spontaneous? The trick is set G, delta G to 0. That's when things are at equilibrium. And that's when it's neither spontaneous or non-spontaneous or norm-spontaneous. It's both. That's the break-even point. And so find the temperature where it's at equilibrium. And then, I'll show you in a minute, actually probably the next slide. Then you have to decide, hey, if you go above that temperature, now is it spontaneous? Or do you have to go below for it now to be spontaneous? Remember at delta G equals 0, both forward and reverse reactions happen. But a temperature degree lower or temperature degree higher, it'll either be spontaneous or non-spontaneous. So that's a cool trick. Remember, set delta G to 0. Look at your equation, your chemical equation, and decide, wait a minute, is that at equilibrium already? If it is, you know delta G is 0 if it's at equilibrium. What's this? Okay, so we have to be a little careful about, I won't do this to you, but technically, if you do some advanced calculations, we'll ask for delta G values at other temperatures beside 25 degrees Celsius. 25 degrees Celsius is well, my computer's really messing up. Is standard conditions. More importantly, is 298 Kelvin. I don't know, sorry. That really messed me up. So what I'm saying here, I will keep things at 298, or I'll warn you if I'm going to switch it. I don't see myself doing that, but that's what this slide is saying. Standard conditions are at 298, and you have to make some adjustments if you're not at 298 Kelvin. We're also assuming 1 atmosphere of pressure and 1 molar concentration. Oh, and this is a really good hint. Because we're multiplying by temperature here, delta S tends to be a smaller number than delta H. So usually you look at a table, if that's what you're given, your delta H's will be in kilojoules, but your S, your enthalpy change, will be in joules. So when you want to add, well, there's a subtraction. When you want to do math on this, make sure you're in the right units. You'll have to convert one of them usually. Like if this is in kilojoules, you might want to switch it to joules, so then it matches the entropy change in joules. Just watch your units. All right, let's try this one. And then we'll actually emphasize the change in units, because this one's in kilojoules, but this one's not. It's only in joules. So this one wants us to calculate the standard free entropy change. Free entropy change means delta G. And what's delta G? You could go back a couple slides and look it up. It's equal to delta H minus temperature delta S. Oh, I know what's going on. I'm hoping I'm going to stop that glitching. Pressing the wrong button. Okay, so let's put it in here. Delta G equals delta H minus T delta S. We want this number, that's our unknown. Delta H is right here. Delta G equals a negative 92.2 kilojoules. Minus T, what's T? Right over here, 25 degrees. But don't use Celsius, you must always convert. Got to match your units. Entropy is not in degrees Celsius, it's in Kelvin. So 25 degrees is equal, add 273, or just remember 298. Darn it, I thought I got rid of that glitching. And then we multiply by this number, a negative 198.7 joules per Kelvin. And this one is in Kelvin. So the Kelvins cancel out. So delta G equals negative 92.2 kilojoules minus, and then I multiply these two numbers together, and I didn't do my math. I didn't show all the steps. I just went right to a negative 33.0 kilojoules. Sorry. Let me grab my calculator real quick. And we'll do that together. We got 298 times 198.7. Come on, Ben, where are you? That was a 59,212.6 joules, but this one is in kJs, kilojoules. So you have to, so what I did is I left in kilojoules. So I divided by 1,000, multiplied 1 kilojoule divided by 1,000 joules. That's a conversion factor. The joules cancel out. That tells me I got to divide by 1,000. So this is 59.2126 kilojoules. There we go. 92.2 minus the 59, whatever, to 3 sig figs is a negative 33.0 kilojoules. Okay, harder problem, more math here. Let's switch over to a screen where I have some room. Here it is. Got that. Here it is. Okay, so in the next self-check, iron metal can be produced by reducing iron 3 oxide, this molecule, with hydrogen, that molecule, to make iron metal. That's what we want. And you make some water as steam. Cool. Is this endo or exothermic? Positive H means it's endothermic, absorbs heat energy. Entropy change, is that becoming more disordered or less disordered? More random, less random? It's positive, so it's more random. Does that make sense? Why? Why lines now? You start with solid gas, you go to solid gas. Okay. You start with one of these and 3 of those. You start with 4 particles, but you go to 5. Yeah, you're creating more particles. That's more disordered. This delta S should be positive. Okay, that makes sense. Is this reaction spontaneous under standard state conditions? Spontaneous, remember, most people react negatively to something spontaneous. We want to know if delta G is negative. Sorry, negative, less than 0. Is it negative? If yes, then it's spontaneous. So how do we calculate delta G, Gibbs free energy? It's delta H minus temperature delta S. We got the H, it's a positive 98.8 kilojoules. Gotta watch those units. Temperature, what are you? 25, standard conditions, which is 298 Kelvin times S, positive 141.5 joules per Kelvin. Good, my Kelvins cancel out, leaving me with joules. The minus sign is still there. This is number 6. So I got a 42, comma, 167.5. Is it? Oh, I multiplied. So I don't know. I didn't write down all the digits, but this is in joules. Got to multiply. I want to convert it back to kilojoules. So let's divide by 1,000 joules, multiply by 1 kilojoules. Joules cancel. Multiply this. Multiply. Divide by 1,000. And then subtract it from 98. And finally, the delta G, I got it to be a positive 56.6 kilojoules. So is this reaction spontaneous? It's positive, so no, not spontaneous. Now, if you ever seen them try and make iron, you have to heat it up. You're not going to do it at 25 degrees Celsius. So nope, we need to heat it up. At what temperature will the reaction become spontaneous? Okay, now we do want to make molten iron. We got to, want to make our own weaponry, our own swords, whatever. So go get some iron oxide, which is a form of rust, iron ore, that red dirt. Go get some of that, heat it up in some hydrogen gas, heat it up so you can actually get this reaction to go spontaneously. Start making the iron metal. Well, how do we do this? Part B. What temperature? I don't know. Let's find out. You got this equation. And the trick is assume you're at equilibrium. Let's find the break-even point. Right now, at 25 degrees, this doesn't happen. But if we heat it up, if it's hot enough, it will happen. It will be spontaneous. So there's a point where it goes from positive G, not spontaneous, to negative G, yes, spontaneous. From positive to negative, it had to cross over 0. Delta G equals 0 at equilibrium. So let's assume we're at equilibrium. Delta G is 0. Delta H, we already know it, it's 98, a positive 98.8 kilojoules. And now, whoops, we subtract the temperature, which is what we want to find out. What is the temperature when this iron reaction is at equilibrium? Well, delta S is 141, a positive 141.5 joules per Kelvin. And now it's an algebra problem. Let's see, what do we do? We got to let's add 141.5 times the temperature to both sides. So then I got T 141.5. I know that should be joules per Kelvin, equals a 98.8 kilojoules. And then let's divide by 141.5 joule Kelvin. Oh no, kilojoules and joules. So before I divide, why don't we slide this over by 1,000? So it's in kilojoules, is that right? Why does that not seem right? Yeah, that's right. I better check my calculator. Yeah, it's gotta be right. Let's find out. 98.8 kilojoules divided by 0.1415 kilojoules, 698. Well, that's a high temperature, but we're expecting a high temperature, molten iron. I got 698.233, whatever. That's too many sig figs. So what do we got? We got 3 sig figs up here. We got 4 up there. Let's just carry 3. So 698 Kelvin is the break-even point. So at what temperature will it become spontaneous? Not at 698. That's when it's at equilibrium. So do you want to go a little bit higher or a little bit lower? Well, this is how I kind of think of it. the break-even point, the equilibrium temperature is 698. That's when you can make liquid iron, you can change in the rust. It's in equilibrium. We did the calculation at 298. 298, and delta G equals a positive 56.6. At 698, delta G equals 0. So where is delta G going to be negative? Well, not this side of 698, because that's where it's always positive. It's got to be on this side. That's where, so you see, you start at 56.6. As you increase the temperature, delta G went from 56.6 down to 0. As you go above the temperature, it's going to keep going negative. So the answer is above 698 Kelvin. It is spontaneous. And you know what? If you have time on the exam, I would check that. So you say, well, let's check. So delta G equals delta H minus T delta S. I want this to be negative, so let's find out if it will be if I go above 698. What's delta H? 98.8 kilojoules minus temperature. Okay, it's a check. So let's check and see if we're right. What's a temperature higher than 698? 699, I know. Pick a number that's easier to work with. How about 1,000? 1,000 Kelvin's definitely higher than 698. So how about we pick 1,000 Kelvin, because the math's easier, times delta S, 141.5 joule Kelvin. I need to convert this to kilojoules, right? H is in kilojoules, my S is in joules. So now they're in kilojoules, but wait, this 1,000 cancels out that 1,000. Yay! If you don't trust me, use your calculator. Multiply this all out. And now you got 98.8 minus 141. 141 is bigger. This is going to be a negative number. Did I do the math on this one? No. Yes, wait, there it is, negative 42.7. I didn't trust myself. I punched it in the calculator to make sure. Yes, it's negative. So spontaneous at, that's supposed to be the at symbol, at 1,000 Kelvin, which is above 298. So yay, that was a nice check. It looks good. Cool. Think you might get one of those problems on your exam? You can bet on it. Yeah, so get comfortable with that one. Let's go back to the PowerPoint slides. Okay, honestly, that's the one I spent the most time on as I was preparing this. That's the hardest question on this whole set. So hopefully that's comforting. We don't have any hairy ones like that after this. Oh, let's go over here. Okay, you happy now? There you go. Yes, okay. Learning check number 7. Take a screenshot and work on this one. You can do this one. It's much easier. It wants you to find the boiling point. So what's your variable for boiling point? What's the thing you're looking for? You're looking for the temperature, right? So you want to estimate the boiling point. So you're trying to find T. And then you're going to use delta G equals delta H minus T. Oop, that's what you're looking for. Delta S. And what happens at the boiling point? What happens? Things boil, right? Liquids become gases. But what else also happens at the boiling point? Gases condense. So I know the boiling point is less familiar than freezing point and melting point. Yeah, freezing point, melting point, same temperature. Freezing points when liquids become solids. Melting point, the solid becomes a liquid. They're in equilibrium. That's the key. So if you're looking for the boiling point, that's when gases go to liquids, liquids go to gas at equilibrium. You're going to set delta G to 0. You got the heat of formation. Oh, that's not bad. I was going to say you have to use Hess's law to calculate the delta heat of the, you do. You have to calculate the delta heat of the reaction. The product minus the formation of the reactants. Do the same thing with delta S. And use this equation to find T. And then you can check your answer by looking up the boiling point of this crazy molecule. What's the name of that thing? Pretend it's ionic and say it's carbon with sulfur, change sulfur to ide, carbon sulfide. Is it ionic? No, they're both nonmetals. Look at the periodic table, they're both in upper right. So that means you have to use the prefix di. And so this is carbon disulfide. Okay, so you can look up the boiling point of carbon disulfide to check your answer. Bring it up in the discussions. We'll compare our answers and our steps that we did it. Hess's law, we just did on the last slide. How do you calculate delta H? It's the products minus the reactants. Delta S, products minus the reactants. Now, delta G, products minus reactants. So there are tables. Let's show you. They're in your textbook. Where did I hide it? Here. Let me make sure that you're seeing the screen. So in your textbook, so over here in the table of contents, right? So here's, table of contents. We're dealing with chapter 12, thermodynamics, but if you go to the end of your table of contents, you get the appendices, appendix G, standard thermodynamic properties, and here's heat of formation, the free energy of formation, and your standard entropy for doing all those Hess's law calculations. So you can look up values here. Very cool. There's a shortcut. If you go on the table and start looking up the elements, like H2, oxygen 2, what else? Helium, iron, they all exist as monatomic atoms. There's other, mainly the nonmetals that like to be diatomic, sulfur 8, phosphorus 4, those are the weird exceptions. Any element, I just listed the elements, in their most stable form, we define the entropy, the free energy of formation equal to 0. Yeah, let's think about it. What's this F stand for? It says how much energy it took or was released when we made the compound. Wait, if you're starting with the element, that's its natural state. We didn't make it. It started out that way. So we're just defining it as the free energy to make the standard elements is 0. Didn't take any energy, none of them released or given off to do it. So that's a nice shortcut. If you see one of the elements in your equation, and you have to do one of these Hess's law calculations, you can say, wait, that's the element. The delta G of formation is equal to 0. And just as proof, there we go, right here. Here's a table as an example. Pen, please. Hydrogen, 0. Nitrogen, 0. Who else is on here? Carbon. Okay, carbon has 2 natural forms, but what's the most stable form? Turns out it's graphite. Charcoal, graphite's found in pencil lead. It's not 100% pencil lead, or is it? No, I think there's clay and stuff in there. Diamond actually takes a little bit of energy to make. It's a little positive here. It's not, yeah, interesting. Huh? Anyways, just be a little careful with some of these elements. I guess carbon's the only one you have to worry about. The natural, most stable form of carbon is the graphite form, 0. Number 8. Okay, that one is Hess's law. You want to calculate the free energy change. Where's my pen, please? There it is. So you're trying to find free energy change, that delta G. And you want this equation. So delta G, Hess's law, is going to be the free energy of formation for the products. And which one's the products? Iron. Oh, wait, that's 0, natural state. Carbon dioxide, it's right here. It's a negative, come on, pen, a negative 394.4, but there's a 3 here. So remember to multiply it by 3 and subtract that from the reactants. And there's a 3 there. And when you do that, I got number 8, a negative 29.4. What are the units? Kilojoules, I believe. Yes. So, is the reaction spontaneous? Most people react negatively to a spontaneous thing. Yeah, this is negative. It's spontaneous. So it's a yes. Explain. It's negative. I don't know what else it wants. Or maybe you have to show your work as your explanation. Okay. Ooh, so we just did all those equilibrium equations, all those ice tables. So chemistry is a cumulative course. Let's bring all that stuff in now. Okay. Remember, Q is the reaction quotient. It's what you calculate K by taking the products concentrations over the reactants. But for Q, you use the values of the concentration or the pressures if you're dealing with gases when they're not at equilibrium. That's how you calculate Q. And wait, if you're not at equilibrium, then the reaction wants to shift forward or backwards. And delta G is saying, hey, if delta G is negative, the forward reaction is favored, spontaneous. And if you calculate a positive delta G, then the reverse must be the spontaneous way. So it kind of makes sense that if you're not at equilibrium, it wants to go one way or the other, which is telling you spontaneous one direction or not to reach equilibrium. So this is the equation that ties free energy into the Q. This is the standard delta G that you would calculate at equilibrium. And then now you're not at equilibrium, so you get the new delta G for this non-standard condition. And you can change the energy now, sorry, the temperature. So standard is at 298 Kelvin. So now you can actually look at different temperatures, but you don't have to. It can still be 25 degrees Celsius, 298 Kelvin. It could just be at non-equilibrium concentrations. Oh, the other thing is non-standard. Let's go back. That might take too long. Remember when we first decided what standard meant? It meant 1 atmosphere. It meant 298 Kelvin. It also meant 1 molar. 1 mole per liter is a standard concentration. So these values of Q could be at concentrations that are not at 1 molar. That's what makes them non-standard. All right, let's give it a go. Number 9. So calculate delta G for the formation of ethylene from carbon and hydrogen at 25 degrees. Ooh, standard temperature. Ooh, but the partial pressure is a 100 and not, so that's not 1 atmosphere. It's not the standard pressure, and 0.1. So yeah, we want to use this equation. And if you use it enough, you'll memorize it, but you don't have to. I'll give it to you on the exam. It's a standard entropy. Sorry, that's not entropy. That's delta G. It's right here. It's the standard free entropy change at standard conditions, 1 atmosphere of everybody that are gases, and you subtract it or add it. I think it's added. Go back one slide. Yes, it's adding. Add RT natural log of Q reaction quotient. Okay, so add RT natural log of Q. Over here off the side, let's calculate the Q. Remember that's products over reactants. And here, let's see, we got ethylene, which it's 0.1. And then the coefficients in front, nope, just a 1, so good. That's the pressure. The hydrogen though, there's a 2, so we gotta square this one. And then what about the solid here? Yeah, solids and liquids don't show up in your equilibrium expression, nor in your Q, the reaction quotient. Cool, so we can crank on that. Did I write that down? I probably did not. Number 9. No, my apologies. If I wasn't paranoid about getting it wrong, I could just do it in my head, but we can put it into the calculator. We're trying to find delta G. This standard, the degree 0 is standard, has standard conditions, and they thankfully tell us what it is. It's 68.1. R, let's go back one slide. R is not, the R you might remember from PV equals nRT, the ideal gas law. It has different units here, which is why the value is different. It's 0.008314 kilojoules per mole Kelvin. That's because delta G is going to be in kilojoules. Temperature is going to be in Kelvin. So we need these units to make all the units match. Okay, so the R was, I think, 2 zeros, 8314, and that was in kilojoules. Mole Kelvin. Times the temperature, what's temperature? 25, that's nice. 298 Kelvin. Times the natural log of 0.1 over 100 squared. And I apologize, I didn't show my math. Check my math, see if I got it right. What I think it is a positive 39.6 kilojoules. And that's all they wanted. They just wanted us to calculate it. Nice. Calculate the free energy change. Okay, so this is more of the same. Why don't we put this in the discussion? Looking at my numbers here, yeah, you follow the exact same thing. The one difference is they don't give you, let's back up one step, Dennis. So you need this equation again. Delta G, the free energy change for this reaction is the standard free energy change plus RT ln of Q. And there's the pen acting up again. This is not given. You got a formation here. So you have to use 2 equations. So you want to use this one, but you don't have this number. So you have to calculate it first. So the delta G is equal to, well, formation. That's your products. Delta G of formation for the products. Well, there's the product right here. And it's a negative 16.5 minus delta G formation of reactants. Do you have to go look these up? No, these are the natural elements. The formation is 0. Oh my goodness, we can just do it right now. So the formation is 2 times negative 16.5. Oh, wow. Sorry about that. Minus the formation of the reactants, which are both 0. 3 times 0 plus 0, yeah. So it's this number, 2 times a negative 16.5, which I think is a negative 33.0. That will go into your delta G calculation. This number will go, no, it goes right here. And it's a plus RT ln of Q. Yeah, this pen does not like the PowerPoint slides. It wasn't messing up on the other program. But anyways, why don't you continue that for A and B, and we'll check our answers in the discussion. Come on, go on. This is basically just telling you how you can look at the sign and kind of see what you already know, right? So when, if Q is mostly reactants, then Q is a really small number. Why is that? Because Q is like K, which is products over reactants. And if you're mostly reactants, then your reactants is a really, 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 really big number and your products is small. And the 1 divided by this million, this whole number is a small number. And that's how you calculate Q. So Q will be a small number less than 1. What do you want to do with that? So maybe it's 10 to the minus 6. And do you remember logarithms? They really only look at the exponent. So if you have 10 to the minus 6, then your natural log of that small number is going to be around -6. It's not exactly because this is the natural log, not the log base 10, but it will be a negative number. And then what can we say about temperature? Is that positive or negative or sometimes no, that's Kelvin. That's always positive. And then R is that 0.008314, which is always positive. So the only thing that can change its sign is Q. So if Q is less than 1, the natural log of it's going to be negative times a positive number times another positive. It'll always be negative, which means your delta G is going to be negative. Is that spontaneous? Yeah. Spontaneous reactions are usually negative. So as you write reactants in equilibrium with products, and you have more of this, we know it's going to shift to the right. And that's what delta G is saying. It says that as written, it's spontaneous in the forward direction. So it kind of nicely tied in there. And then we can say the opposite if we're mostly product. And once reverse, delta G is positive and says, wait, the forward direction is not the right spontaneous reaction. Reverse it and it's spontaneous. So it needs to go backwards. If you have too many products, it needs to go back and make more reactants. And then you got delta G equals 0 at equilibrium. And it's just reiterating what we just went over. Ooh, number 11. We're getting near the end here. At 25 degrees Celsius, the KSP for lead chromate is 2.8 times 10 to the minus 13. Calculate the free energy change at 25 for this reaction. Did I skip a slide? Because we don't have a Q. We actually have the K. Yeah, I skipped it. Sorry. What's it saying? Oh my goodness, I just breezed on by. If you're at equilibrium, delta G is 0. So let's put in a 0 here. I totally skipped this. I apologize. But you're at equilibrium. So you're not at the K, you're at the Q. You're not at the Q, you're at the K. You're at equilibrium. So your reaction quotient is the equilibrium constant or the equilibrium expression. And so that's getting pretty messy. We have 0 equals the standard free energy plus RT natural log of K. Well, just subtract this from both sides. And you get this fun equation, which is actually pretty cool. If you know the equilibrium constant and the temperature, and we have R, 0.008314, you can calculate the free energy. And if you know the free energy change and you know the temperature and R, you can calculate the K. So as long as you're given all of these except for one, it'll usually be either the equilibrium constant or the free energy that you're missing, you can calculate it. That's pretty cool. And actually it gives you a hand on the lab. If you really wanted to do some measurements, you can calculate the free energy by measuring the equilibrium constant or the reverse. If you know the equilibrium, if you know the free energy, you can get the equilibrium constant. Very cool. That's where this is going. So we're given the equilibrium constant and we want the free energy. So because you're at equilibrium, we can use we can use this one. The standard free energy is equal to the negative of RT natural log of K. And so it's minus 0.008314 kilojoules. No, I'm sorry about that. Mole Kelvin times the temperature, which is 25 degrees, so it's 298 Kelvin, times the natural log of the KSP, 2.8 times 10 to the minus 13. Pretty sloppy, sorry. Put that in your calculator and see if you agree with me. This is number 11. I got a negative 71.6 kilojoules. Yeah. Thermodynamic data to calculate KP. Okay, so this one takes more effort because we want KP. So we're going to use this one. We got 25, so we know the T. We already know the R, that's 0.008314. We need this number so we can find K. We don't get that number. We get delta H and S, right? So we're going to have to use Hess's law twice, right? So you're going to have to find delta H, which is heat of formation products minus the heat of formation, the reactants. Do the same thing with delta S. It's the entropy change of the products minus the entropy of the reactants. And then you can use this equation to find the free energy that you can put into this equation. Clever, huh? Okay, so we'll save that for the discussion as well. If you want to check your answer, I definitely want some help with this one. I'm not sure I trust this. I got a crazy high number, or I'm sorry, it's a very low number. I got 6.7 times 10 to the minus 27. I don't know if I trust that. I need to check my math. See if you get a number like that. Let's post it in discussion and we'll double check our math. $13, this is looking just as ugly, but it's not. Okay, so you want to calculate the equilibrium constants. You want K again. So you're going to use this equation, right? Delta G equals negative RT ln of K. So you want this. 25 degrees, so we got temperature, we know R, 0.008314. Delta G, it's right here. We don't even need these. That's just distraction. So this is trying to test the students, see if they really know what they're doing. You need to use Hess's law on the free energy. That should have been formation, comma, products minus delta G formation of reactants. So find your delta G from this middle column of data. Here's your product, there's your reactant. Don't forget about that 2 in the reactant side. Put it in the delta G up here. You know R and T, solve for the ln of K. You remember how to undo the ln? Let's say if you got, oh, what did I get? I did the math and I got 10,000. No, I didn't get 10,000. I didn't write it all down. I think that is 10,000. Was that 10? That's 10, sorry, not 10,000. 10.13088 equal to the ln of K after I did some algebra. And what you want to do is raise everything as a power of E. That's how you get rid of the ln. You raise this side to e to the ln of k is equal to k, and then e to the 10.1318 tells you that k, I calculated k to be about 2.5 times 10 to the fourth. Another question for the discussion session. Couple of reactions. This is our last slide. So this is kind of cool. Do you remember using, was it also Hess's law? Another version of Hess's law when you had two equations? Oh, I should have written an example down. We had one at the beginning of this whole lecture. We said that we had electrolysis. And reaction one, we said was liquid water going to, wow, my pen is like dying here, hydrogen gas and oxygen gas. We said that is non-spontaneous. You can burn, explode hydrogen gas with oxygen to make water, but liquid water doesn't decompose like that all by itself spontaneously. So this is non-spontaneous as written. But you can use a battery. And the battery action is spontaneous. So reaction one's non-spontaneous. So the delta G of the first reaction is going to be a positive value, non-spontaneous. This one's going to be spontaneous, so it's going to be negative. And then if you couple them, do them connect them together, get both reactions going together. If you add them together, this positive one and this negative one, if this is a larger negative, like if this is a +5 but this is a -100, then delta G equals -95. Hey, the sum is negative, which means together the reaction is spontaneous. The reaction happens all by itself. And that explains why, go back to this one, we got this cool picture of a battery creating bubbles of hydrogen gas and oxygen gas spontaneously. Together with the battery and the electrolysis, the coupled reactions is going spontaneously. This is one of nature's favorite tricks. So we do it all in our bodies all the time, right? So it's spontaneous for things to rot. Leave your mashed potatoes outside for a couple days, mold builds up, it's going to degrade, decompose, spontaneous. It's the free energy is negative. You eat those mashed potatoes, your body finds it easy to break it down and get energy out. Awesome. But what about a plant who's making that potato? To make the potatoes, for the mashed potatoes, that's non-spontaneous by itself. You have to take small molecules and make them into bigger ones, make it more complex, make it more organized. It takes energy, it's endothermic. That's not a spontaneous reaction. So a plant has to couple it with photosynthesis, bring in light. The absorption of light is spontaneous, energy producing, couple it together and using the energy of the sun can drive the reaction to make a potato that in itself would be non-spontaneous. Cool. All righty, thanks for sticking around. I'll see you in the discussion group.